SwayamPrabha. Digital India. Educated India.
Start fluidization, that is one, fluidized bed reactors. Take the definition. Fluidization is the technique in which fine solids are transformed into a fluid like state through contact by a fluid. In the bracket you can put either gas or liquid. Okay. So, the phenomena we will discuss through the diagrams. I will draw these diagrams so that the picture will be easy for you to understand. Gas or liquid, then we have this one we call it as HP, packed bed height. Okay. Able to see, Kavya? Okay. So, this is HP, height of the packed bed, and at very low gas or liquid velocities, there is not sufficient energy in this phase, fluid phase, where it can move the particles, but on the other hand what it does is it only tries to find out where is wherever there is a small interstices, through that it will move and comes out. Okay. Nothing happens at that time, the bed remains as a bed, and of course, depending on very low flow rates, one can also measure the pressure drops, that I will draw the graphs later. So, at a particular point, this situation, this is fixed bed, we can write fixed bed, then same thing gas or liquid. When you have this is the height, still you have the particles very close, just see here, just a little bit more height, this is HMF, height at minimum fluidization velocity. Okay, good. So, this is okay. So, as I told you, when you slowly increase either gas or liquid, nothing will happen at very low fluid at low velocities, only the gas or liquid try to percolate through the pores, and then when you go on increase very small increments, then the gas or liquid at one point of time, the drag force exerted by this fluid either gas or liquid will exactly balances the weight of the solids in the bed. Okay. So, drag is a force, weight in the gravitational field is also a force. So, when both the forces are same, drag force balanced by the weight or weight balanced by the drag force, then you will have the particle movement a little bit, the particles move a little bit, but still the bed is not expanding that much, the particles try to readjust themselves, okay, for a more easy in a relaxed manner. So, then it will try to move in that restricted place a little bit, like small vibrations, small movement of the solids. So, at a minimum fluidization velocity, if you look at the bed, it is not exactly like a vigorously solids moving, but definitely solids will readjust themselves, but capable of moving even at that time, but not to a great distances, and the distance between each particle is also not that much. That is the reason why you have anyway this side and this side, it cannot expand, it has to only expand in this direction. That is why I put this is packed bed, it is slightly less because of the readjustments, okay? Just because of the readjustment a little bit more, but all the time we will take Hp also equal to Hmf at minimum fluidization conditions. Okay? But here at this point of time, if I want to test the characteristics of this bed, if I put a, let us say, an iron ball, right? Yeah, at this here, after the weight is balanced by the drag force, if I put that steel ball, then that will simply sink. Just for a comparison, if you do the same thing here, when the bed has not yet fluidized, that means it is still in packed condition, what will happen? It will simply stay at the top. So, that means the density difference has come, and yeah, not only that, in fact, if you have the cork also, cork will just simply float exactly like it is in water. Not only that, you have if you have a small hole here, then it flows like a fluid. Okay? So, just at the time of minimum fluidization velocity, at the point of minimum fluidization velocity, try to have a hole here, side wall. Okay? Then it comes as a jet. It is exactly like if you have water in a tank and then put a hole, then it comes as a jet. And also one more property, if I slightly tilt this, okay, instead of putting vertically, if you slightly tilt like this. So, when you tilt this, but still your surface will be horizontal, whereas that is not possible here in the packed bed conditions. So, that means what is that we have done already? We have spoiled it, because I think it was very happy, stable, without moving. So, then we made it as a fluid where it can easily move, right. All the fluid properties it acquired, like density difference, something can sink, and also something can float, and when you change the direction to any inclined position, but still all fluids maintain horizontal surface, right. So, same thing is there, and if you put a small hole, then it will come like a fluid. All the properties what we normally see for fluids are seen for the solids in the presence of another fluid. That is the reason why it is called fluidization. Okay? That means you are imparting fluid properties to the otherwise immobile solid particles. Okay? Tremendous advantages, okay, because of this. The first fluidized bed was in Germany, Winkler gasifier. I do not know whether you have studied in chemical technology. Winkler, WINKLER, Winkler gasifier, that is one of the first applications of fluidized bed. Then later applications came to your FCC, fluid cutter cracking. So, from then onwards unlimited uses of fluidized beds, but in the beginning is first the gasifier. I think that was 1921, 1922, I think that time, I am not very sure exact. So, the advantage of this fluidized bed is that now you can, if you want, you can easily transport the solids from one place to the other place, and particularly in chemical engineering all the operations are multi-phase, and you should have better contact between these two phases. Now, we have either solid or liquid two immiscible liquids, or gas liquid, you will have all combinations of the phases in chemical engineering. So, our idea is how to have the best contact between these two phases. So, that kind of excellent contact will come here if I have a solid phase and then either gas or liquid I am trying to use. Okay, excellent contact. And theoretically speaking, if I look at the particle in an ideal fluidized bed, each particle is simply suspended by the fluid. So, that is why, like our fluid mechanics, we always draw one beautiful circle as a particle, around that you will show very nice streamlines. Okay. So, what is happening when I show the streamlines, whether it is a heat transfer process, whether it is a mass transfer process, then beautifully each particle is uniformly either taking, if it is a mass transfer, absorbing, or if it is coming out from the leaching and all that. So, beautifully comes out. Heat transfer also same thing, heat is uniformly transported. And on the other hand, if you look at the packed bed of the same height, what happens? Packed bed is resting one above the other, all the particles, right. So, that means always some contact area will go for the solids. That contact area is not available in the packed bed conditions. Okay. Talking about the same particle size, right. And normally we use the particles, very small particles in a fluidized bed to take care of our surface area per unit volume advantage. That means, when you are going for smaller and smaller size, surface area per unit volume equation is 6 by dp, diameter of the particle, surface area per unit volume. So, when you are decreasing particle size, surface area will be tremendously increasing. Okay. So, if you are going for 1 mm, then 0.1 mm, 0.01 mm, 0.01 mm is 100 microns, right. 10 microns, 10 microns. So, then go to 1 micron, then you will have tremendous surface area, and we can use that kind of surface area also for the solids. So, that we will get very high transport processes, right. Good. So, that is the one. Now, till here we are almost in ideal conditions. This is fluidized, but beyond that, if you increase, what will happen? Beyond that, if I increase, let us first say only I have liquid. Okay. The behavior from here, the behavior, if I use liquid as the fluidizing medium, or if I use gas as fluidizing medium, the behavior changes. That is why first we are taking liquid. So, if I take liquid and then go, for example, at this point I can also say that I have UMF, the velocity corresponding to this minimum fluidization condition is UMF. So, beyond this, if I go and let us say I am using 2.5 times or 3 times UMF, right. So, then if I use that, then beautifully this expands in the presence of liquid. Why I am telling beautifully is the interparticle distance between the the interparticle distance in the bed is almost uniform when you have liquid, and that is why we call this one as smooth fluidization or particulate fluidization. Particulate fluidization, right. It is very nice to see. One can easily predict also the length of the bed, how it is expanding, and we can just imagine here, beyond minimum fluidization velocity, the drag force of course is just balancing. So, beyond that you are increasing velocity. So, drag force will be definitely more. So, when it is more, what is happening, how it is transformed? The drag force is transformed in the form of expanding the bed. Okay. But if you take the pressure drop, I will come to the pressure drop later, at this point onwards you have the same pressure drop for the solids. Weight is not changing, right. I mean, weight is same, weight is not changing. So, keeping the weight same, and when you increase the drag force, okay, by changing the liquid, by changing the liquid velocity or gas velocity. So, the pressure drop is not going to change, only thing is in the bed you will have different conditions coming, right. So, like that it is in the particulate fluidization condition, the pressure drop will not change, but the bed can be very smoothly varying. Now, the same situation if I show for gas, it is not so smooth. So, you will have here a bed, these are the bubbles. So, you will have small bubbles forming here, growing like this. Even though we take spherical bubbles, they are not like that. Yeah, this is the bubble. Gas bubbles will form, and these bubbles are not seen in the liquid solid fluidization. Okay. And the reason for the bubbles, I think we do not know yet exactly, but we know how they form, because whenever I have a perforated plate and with a small perforation and the solids are just resting on that, the gas has to move through that. So, when it is moving, it will try to push the solids slightly away from its way. So, when it is pushing, so then there will be a wall like thing just above that area. So, that wall, this wall is nothing but solids only just forming like this. So, when it is just pushing it up, then they form that wall, and the wall cannot break, because just after that also you have a lot of solids. So, it is not breaking. So, the entire bed almost in the small void there, it will try to push it up, and beyond here at the top, because there are no further solids there, then it has to break. And when it is breaking, then all the solids, till then it is just moving like this, okay? Yeah, just moving, and then when the bubble breaks there, all the solids now cannot be supported by anything, there is nothing to be supported. So, they simply fall. When they are falling, they come to the bed. That is how you have good mixing in gas solid fluidized beds, because of this bubble formation, and the bubbles are not there at minimum fluidization velocity. That is why at this point, whatever gas you have, all the gas is used only to support the solids, but here when I have that 2.5 times or 3 times, as I told you, the gas velocity, then that extra gas beyond what we use for minimum fluidization velocity, extra gas beyond minimum fluidization velocity, that goes in the form of gas. So, that is why many researchers accepted that if I am sending u as the velocity, and the velocity at minimum fluidization is UMF. So, u minus UMF multiplied by cross sectional area is the volume of gas that is in the bubbles, correct? No, u is the actual gas, let us say 10 liters, okay? I mean velocity wise, and now directly I can tell volumetric flow rate wise, and I need only 2 liters per hour or 2 liters per minute as the gas required for minimum fluidization velocity. So, that extra 8 liters per minute is the gas that is going in the form of bubbles. Okay? It is not exact measurement, but I think this is very difficult contacting pattern for gas solid, right. So, that is why it is not exact. Many people say that no, some other gas is going this way, that way, still fighting is going on, but still majority of the gas goes only in the form of bubbles, and our imagination is that there is no other way to go to go for the bubbles, okay? I mean for the gas to go. So, that is why either it has to support the solids and go, otherwise it has to go as bubbles, right. So, that is the reason why you have here a kind of aggregative fluidization where it is not uniform, because why it is not uniform, where the bubbles form, where the bubbles break, you cannot say. In fact, when you have this situation, you can do that experiment in your house also. Take a water put in some vessel and then bubble it, just look from the top. Can you find out at what point bubble come and then what point bubble breaks? You cannot. Same thing happening. So, that is why some people say that this is also boiling solids. We do not see the bubble, we see only the wall, the empty space in the solid. The empty space in the solid is seen as bubble, okay? And people have photographed. I will also show you that photograph later. Okay? Some photographs have been taken, and I think people thought that there are definitely bubbles. Okay? It is that is why many people still have lots of doubt. If gas liquid one can see, that is what normal things, those are all low hanging fruits, what we say. Okay? When you are able to imagine, when you are able to see very clearly, okay? So, then the description of that, understanding of that is much easier. But something beyond our mind, if you are not able to see, and then you have to imagine. Okay? So, that is why a measurement is required where you, because you are not able to see that. Of course, you can see that when you have a glass column, but I think that voids and all that definitely can be seen. But to be still perfect and measure it and then find out what kind of bubbles we are getting, why they are coming, under what conditions, like for example, that also depends on your velocity, that also depends on particle size, okay? Particle density, all kinds of things will come, how the bubbles are forming, right. Good. So, that is why this is not no more smooth fluidization, this is called aggregative fluidization. Aggregative. So, essentially what we have to remember here is that till minimum fluidization velocity, whether you have gas or liquid does not matter, because both are going to behave same way. And then beyond that, when you are using liquid fluidization, liquid solid, where liquid solid applications also after biochemical engineering there are many. For example, wastewater is one of the applications, liquid solid systems in fluidization, in using fluidizer beds. Okay. Of course, leaching, one method of extracting ores is leaching. So, if you want to take from copper from copper ore, you take copper ore and then fluidize with sulfuric acid, for example, you will get copper sulphate, and again copper sulphate you take it to electrochemical cells, and then sulfur SO4 separately, Cu separately, you can deposit, right? Yeah, Cu. So, then you get one of the purest form. That is how zinc and copper and all kinds of things they do, but that is the leaching operation where fluidized bed can be used. Why fluidized bed is very good there is that you can have small particles, number one. In packed bed you cannot have that kind of particles, and number two, surface area is more. So, then the rate of leaching will be very high, and on the other hand every particle will be uniformly fluidized, particularly when you have liquid system. Then on the whole each and every particle is uniformly leached out, that can be used for leaching each and every particle. So, like that there are many examples which we can give, and liquid solid, and there is not many exciting things in liquid solid, because everything we know what is going to happen there, correct, no? Because there are no bubbles, whereas here many exciting things, because first of all I do not know how to measure the bubble perfectly, and the people who have measured the bubbles are only 2-dimensional bubbles, what they measured. 3-dimensional bubbles they could not measure, they only estimate by some technique, okay, by sending light, for example, or by sending some not tracer, not NMR also, this one radioactivity, some signals they send from this to that side. Nowadays I think people trying to use what is called TEM, transmission electro, yeah. So, that kind of sophisticated methods are now coming to measure, okay. And that to measure, it is when you have a 3-dimensional column, you will have some bubbles here, back side also you have some bubbles, this side also you have some bubbles, this side also you have some bubbles. Which side you measure? Whatever side you focus, that is not uniformly reproduced all the time, okay. So, that is why they take from various sides and then average the bubble size. Bubble size is one of the most difficult parameters which we have to estimate properly, and that itself is the starting point for all our calculations. So, that is the reason why it is very difficult gas solid fluidization, okay. Good. And because it is very difficult, there are challenging things. If it is very simple, I think there is no problem at all, because there is the phenomena is so complicated. That is the reason why I told you that you have many exciting things in gas solid fluidized beds. Okay. Then next one, if you have, let us say I have done the same thing here beyond this minimum fluidization velocity in a small this kind of column. Okay. Very narrow column, if you take narrow cross section, then what you see is these bubbles occupy the entire cross section, and then somewhere here they break because of instability. Okay. Yeah. So, these are the please remember, you have when it is going up near the walls, you will not have that much drag, because velocity we take 0 near the wall. So, the solids will be slipping near the wall, somewhere it will go up, and then because of some instability it will go to almost to the top, okay, if there is no disturbance. But somewhere if you have disturbance, means many chaotic conditions. That is why I do not know whether you heard of, there is what is called a chaotic theory. For each and everything there is chaos in this world, in this universe, not only world. So, that is why maybe with very small fluctuations or very large fluctuation. Large fluctuation means we feel, small fluctuation means we do not even notice them, but everything can be analyzed in terms of only this kind of fluctuations, right. So, chaotic theory, that means system is not stable, it is chaotic, but people see that there is an order in the chaotic environment. there is still an order. Now, if you go to Mount Road and if you stand there for some time, first time it looks very chaotic. I do not know why people are going this side, cars is going this side, I think bullock carts might be going that side and all that. You observe that, let us say 1 week, you will find a pattern. How? How do you find a pattern? The same 18B bus will come all the time. Okay, really 23C will go there. So, if you are able to look patiently there, you see some pattern coming. Maybe there is some bench car, that same bench car, because that fellow's office may be somewhere there nearer. Okay. So, always when you patiently observe that, you will find a pattern. So, that is what order out of chaos. I do not know whether there is a wonderful book which I could not complete in last 20 years. I think I told you. James Gleick's Chaos, that is a beautiful book to read. The other book is that Ilya Prigogine. Heard of him? Prigogine, Prigogine. He is a Nobel laureate in chemistry. He wrote this book Order Out of Chaos. Okay. Actually, he wrote that in French and someone translated into English, horrible translation, because that is why I think nothing moves there. There is no flow in that book. Oh my God, how many years I have that book? I am not able to still complete. But there is wonderful information about thermodynamics, about biological systems, all order and how do you see, all chaos, how do you see order out of that. James Gleick is beautiful book. Once you start like a novel, you can read. Okay, but the other book is very, very difficult, where tremendous amount of information is there, excellent information. So, that is why here also, because of those fluctuations, somewhere because of instability, the slugs will break and then all the particles will come down. When they are coming down, again some of the bubbles also may be broken, and that is why some of the fluidization researchers thought that let me take, because you see how human mind works, because to break the problem into simpler problem. So, is it difficult, is it easy to have 1000 bubbles and then try to characterize 1000 bubbles, or one bubble and then try to characterize one bubble? So, that is why what they did was, okay, let me take the small diameter column, okay, let me create slugs and let me understand how the slug, because there is only one slug any time, correct, no? So, that is why, but most of the time what happens is, when you have this kind of thing, it is too much aggregative fluidization and this is a big void. Most of the time in the bed, if you see, there will be only 20% or 10% solids, the rest is only gas bubbles. One bubble, that means one bubble here, another bubble there, another bubble there, maybe 5-6 bubbles will occupy, but that bubble is very slug, very lengthy bubble and occupying the entire cross section. So, it is not allowing to solids to have many solids. So, that is why they try to break it, particularly Australians, there are few who are trying to do that, and this is called slugging bed. Yeah, there are many things here, this aggregative, as I told you, when you have more and more knowledge, you also try to look more and more narrowly between velocities. Okay. Between aggregation and then if I go slightly more than that, what we call as turbulent bed. Okay. The difference between aggregative and turbulent is the bubbles are slowly trying to dissolve. Okay. Dissolve what? Dissolve to go for pneumatic conveying. That means, when around terminal velocity, the bubbles may disappear, solids may try to go out. Okay. So, another concept is, I think definitely you would have heard of circulating fluidized beds. Circulating fluidized beds, no, not heard? I told 1000 times, I say, in the last semester also. Anand Kumar looks as if it is a new word for him, Latin or Greek. You have not heard? Do not remember. Okay. Yeah. So, you allow the entrainment and then bring the solids again continuously and circulate them. Okay. What is the advantage? Because now I do not have bubbles, I can clearly find out what is happening at least in the bed. But what is the drawback? Drawback may be that the amount of solids in the bed may be small. So, normally it happens around 15% solids, 20% solids, whereas here I have 50% solids and also 60% solids. Okay. 60% is more, around 50%, because normally packed bed will have how much, what percentage, packed beds will have what percentage of solids? Normal packing, spherical particles. Kavya? How can you have 80% in packed bed? Packed bed has also porosity. Which one is 60 you are talking about, void edge or solids? I have asked solids. Void edge is 60%. Abhinav, Anurag? Call it, solids. What did you say before that?
40 to 50%.
40 to 50%. Why 40 to 50%? It is a packed bed. Under what conditions it will be 40? Under what condition it will be 50? Renita? Prabhu will give a nice answer. Prabhu, what?
65% solids, sir.
5% increase. 65% solids. Why 65%?
So if you say 60-20, then you lost when 60 when 70.
Told you, no? Beautiful. That is the reason I asked you. At the end, you are the final answer. Okay? Yeah, always averaging things. Okay, I think like Buddha's thing, take the middle path. If you take extreme path, you have to unnecessarily work hard. Take the middle path, happy, no problem. No one can push you that corner, no one can push you this corner. Walk. Okay, Buddha's fundamental thing, it seems, take the middle path always in your life. Don't be an extremist. That is the idea. Okay? Yeah. You tell me why 40 and why 50? 65 is not correct. 45? Huh? See, in material science they derive and then show it also. I say, if you have ideal spherical particles, how much fraction you get? Huh? Size it will not depend if you have spherical particle. Shape is spherical, I am telling you, no? Yeah, spherical. Exactly, there is around 0.32 or something you get. Structure if you take, that is void edge I am talking. Void edge is around 32 and you have 60% solids. Okay? In packed bed, because they are not 100% spherical, most of the time we can take around 40% void edge and 60% solids. If I take 100 liters, I will have 60 liters of solids and 40 liters of void edge. Okay? So, that is what. Yeah. So, that is why now the operations depend on what regime you operate. Like for example, next one is we have pneumatic conveying. Here again it is same, either gas or liquid. Again you come back to the original, to this end. Okay. So, when you go to the pneumatic conveying, you have only few solids, that is pneumatic regime. So, that means solids are, we say pneumatic regime, but I think hydraulic regime also we will say, where the transportation of solids are occurring because of water, okay, liquid. So, this is pneumatic again, but does not matter whether you have liquid or solid, you will have this. So, what are the basic conditions here? Basic conditions for fluidization, first of all, it should be vertical. You should take a vertical column, okay, and then put a distributor plate, and then the distributor design also is one of the very important crucial factors, and then slowly increase the velocities such that the entire bed is supported by the drag force of the fluid, and beyond that if you increase, then if you have a liquid system, it nicely expands. Nicely expands means anywhere smooth fluidization and the interparticle distance is uniform throughout the bed, etc. And if you take the same condition, that means 2.5 UMF or 3 UMF, and then conduct the same thing with gas, right. So, the gas will have aggregative fluidization, where the gas goes in the form of bubbles. So, that creates aggregations, and that also creates good mixing. In fact, you will not have that kind of good mixing here. You will have here very good mixing for solids. That is why Levenspiel says that phthalic anhydride is the plant where chemical engineers design. It seems any chief engineer designing phthalic anhydride plant, okay, if you ask them to sit on the plant just before startup, It seems he says that very few chief engineers would have left in the world, because definitely something will happen and explode. Chief engineer will be converted into some other mass. Okay? Yeah, maybe evaporate, anything can happen. So, that is the reason. So, for that, to control that kind of heat, that is generated, if you want to dissipate that heat, this condition is the best condition. Okay? This is what they do, circulating fluidized bed. Before circulating fluidized bed, there was fluidized bed combustors. I do not know whether you heard of them or not. These are not myth, they are reality, where they are working in thermal power plants. What they do is, they take very big size fluidized beds, fluidize coal, continuously feed the coal. I have told here batch only, but continuously also we can do that experiment, nothing will change. Okay? If you are maintaining the same bed and all that. So, coal particles will be continuously fed and burning, combustion is taking place. Now, you put inside heat exchangers, cooling coils. They are not actually cooling, water pipes, water tubes. So, then water will get evaporated to steam, that steam will come out after getting sufficient steam, then that is attached to your steam turbine, the turbine is attached to generator, from there we will get AC and all that. Okay? Yeah, really. So, that is why fluidized beds, when compared to other beds, this is very easy, because particularly what happened was, when people started thinking about environmental pollution, if you have SO2, S as the one of the constituents in the coal, that will become SO2, SO2 will come from the chimneys, that is dangerous. Okay? That is even spoiling Taj Mahal. Okay? Sulfur falling on Taj Mahal, because how sulfur is falling on Taj Mahal? Yeah, where is acid there? Madura refineries. Madura refineries also will desulfurization, there is one step. So, the sulfur has to be removed. So, if you are not able to contain that only inside the reactors or inside the process equipment, when it comes out, then this acid rain will fall, and unfortunately Shah Jahan used calcium carbonate, which is reactive material. It is not inert. If he has used granite, nothing will happen, whatever you do. Okay? Yeah, granite also will slowly dissolve, some other things. Yeah. So, this Ca calcium carbonate reacts with H2SO4, forming calcium sulphate. So, after some time you will have calcium sulphate Taj Mahal. Okay. So, even now if you go and layer by layer, if you see, probably already first 1 or 2 mm or 3 mm, 4 mm would have gone. Okay. So, that is the problem. So, at that time what they thought was that the sulfur can be contained, and also NOx is a problem. All these things are problems now in pollution. So, with the temperature control, you can control NOx, you can control SO2 and all that. And another beautiful advantage in fluidized bed to remove sulfur dioxide is, you do not allow that one to go to chimney. What you do is, when you are sending coal continuously, you also send along with coal calcium carbonate, Taj Mahal only. You make powder, you make powdered Taj Mahal and then put it inside. What will happen? Because at that temperature, calcium carbonate going to calcium oxide is very, very fast. It is the non-catalytic reaction, which you already discussed. Type C reaction, CaO. CaO will form, that is instantaneous. What do you call that? Calcination. Calcination step is instantaneous. Then that becomes CaO. CaO is highly reactive. And you have in the coal sulfur. From sulfur will react with oxygen in this, because combustion, you have to send oxygen anyway. So, sulfur dioxide will form, CaO plus SO2 plus half O2 will give you CaSO4. CaSO4 is now solid, it is not going to Taj Mahal now, it is only at the bottom you will collect and try to use CaSO4 for something. Okay. CaSO4 is nothing but gypsum, no? Yeah. So, that depends on hydration and all that. Okay. So, anyway, that can be used. That is the reason why they were only trying to convert the problem gaseous pollution into solid pollution, because if you are not able to use this calcium sulphate, that is gypsum, then that is a waste again you have to dump somewhere. when you dump it again, because calcium sulphite is a unstable compound, calcium sulphate is stable, and sometimes calcium sulphite also will be there in this conversion. It is not 100% converted to calcium sulphate. So, that will leach out, and then sulphur again will go into water and all that. So, we are doing a wonderful job as chemical engineers, polluting the entire world. Okay? That is what is our great contribution. Other things are great there, but this is also one of the greatest contributions now. Huh? Yeah, unless you prevent, you have to prevent. That is why only we have green chemical engineering, green chemistry, all that. You have to do it. Okay? Yeah. So, that is why please show some interest in chemical engineering. Okay. All of you, I say. All of you. Where is interest in chemical engineering? I say, if you have real interest in chemical engineering, you cannot ask for only marks. You will ask for a project, sir, I want to do this, I want to do this, I want to do this. How many projects are there? How many things are there? Are you asking anything? You are not asking anything. No, now you play everything. You take tennis bat where it is manufactured by nanocarbons, carbon tubes. Yeah, and then you play very well. And with nanocarbons also, I think some dresses, many things are made, and you don't know who has made it, and then you only play cricket, tennis, and then throw the tennis bat out. Where is the pride for you? I made it. As chemical engineer, you made it. Okay? Even you use car very happily, driving or running or all that, but you never feel that it is running because of petrol which you manufactured. Where is the pride for you? There is no pride. Why there is no pride? Because you are not involved. Very simple. My logic is very simple. If you are involved, you cannot stop staying that. Every time you see that, oh, petrol, chemical engineer. Okay? So, anything like that, cement, building, whenever I say building, beautiful, chemical engineering. Yeah, really. Even computers, computer science people think that they are doing so many wonderful things. They can only do provided you give the floppy disks for them. Yeah, hardware, yeah, materials. Okay? This CDs and all that manufactured by us. But still you do not even know that, you are not proud of it. Okay? So, that is why history is very important, what earlier people have done, what you are going to do. So, that is why you are not involved. I think happy, okay, whether it comes in the examination or not. That is all. That is the sole motto from joining date 1 to finally till you get in the SAC building that that degree certificate called in the convocation, degree certificate, that useless paper, right. That will be useless if you do not know anything in that field, I say, really useless. Okay. So, but anyway, these things I am repeating so many times, but in your mind all these subroutines are going on thinking that this idiot is talking all the time same thing. Okay. Yeah, this is matrix, no. So, you are in your own matrix scolding me that this fellow tells only this, nothing else. Okay, good. Yeah. So, this is pneumatic conveying, and now the fluidization, yeah, beyond somewhere here you have it. If I take that as ut, terminal velocity, your fluidization range is from here to here. That is why, as I have been telling you all the time, you have the flow, what is that? Flow regimes. Even here we have a flow regime. Beyond this, no one can operate that as a fluidized bed, and beyond this also no one can operate till here. Yeah. So, beyond this also no one can use that one as a fluidized bed, because it is not simply fluidizing. So, that is the range of fluidization, but in between you have so many operations like this is normal conventional fluidized bed, then you have slightly turbulent or aggregative fluidized bed, then you have here in between I have not shown you circulating fluidized bed. All that depends on how much solids you have in the bed, right. Aggregative fluidization and turbulent fluidization and normal fluidization, you will have 60% solids, 50% solids, 40% solids till aggregative, and also turbulent. Beyond turbulent, the particle starts coming out. So, at that time you will have around 20%. If you are able to operate around 20%, then you have circulating fluidized bed. Beyond that, if you go to only 3% solids, 3% pneumatic conveying, normally we get that. So, then you will have pneumatic conveying, and beyond that no operation is feasible. So, all these things are there. Okay? Good. I know none of you will write all these things, because why? What, Anurag? Yeah, I don't know, you don't write. Yes, sir. Correct. Because you think that this is simply waste of paper, waste of pen. Okay? Why should I write? Because it may come or may not come in the examination. Till then is my duty. After my duty is over, that is all. Who wants this? Throw the particles and books and then go and join somewhere else. What a great generation we have, I say. No respect for what we do, what we are supposed to do, not what we do, what we are supposed to do. Okay? All of you, I am not only talking about them. Okay? They may throw this that book 10 kilometers away, you may throw 1 kilometer away, that is all the difference. Okay, that is all. That is why it hurts us, most of the time, because when we are excited and then telling, you sit there like a statue, probably statues would have reacted. Okay. Real statue, if you take and put there and then talk 40 hours, probably it will have some kind of movement there. But here you have movement, become finally statues. Okay, good. Yeah. So, now if you want to understand these fluidized beds, we need some parameters. Yeah, I think anyway, before that I think we will have the advantages and disadvantages. What are the advantages in using the fluidized beds? Yeah. Okay, good control of solids, that is one. And then excellent heat and mass transport processes inside that. Okay. So, heat and mass transfer rates are very high in the bed, that is one. Smooth and control flow of solids, and number 3 is isothermal conditions which prevent hot spots, isothermal conditions which prevents hot spots due to vigorous mixing of solids, What are the disadvantages? Because I think whatever you do, definitely there will be some particle collision, some powder will always generate, right. So, due to attrition, that is a disadvantage, that is called attrition. Due to attrition of solids, because we are talking about this one as a reactor. So, the catalyst may go out of the, due to attrition of solids, so the weight of catalyst may decrease in the bed, that will come, which pressure drop is more. Okay. Then what is the other disadvantage? Attrition is one where you lose solids, right. Yeah. Anurag, any other? Why pressure drop is bed is high? In packed bed, what is happening? In fact, packed bed gives you more pressure drop than fluidized bed. So, that is why pressure drop is not a problem, because if you are using the same velocities, okay, like 2.5 minimum fluidization velocity, like that, the pressure drop in the packed bed will be much more than fluidized bed. Pressure drop is not the disadvantage. So, then anything else? Range of velocity is UMF and UT, because beyond that you cannot go. Particle diameter. Yeah.
And then after a certain point of diameter, you have to throw gas at a very high flow rate.
Yeah, but that is not disadvantage. No, that is only possible operational regime. Okay, that is not a disadvantage, because no one would like to have atoms to be fluidized.
But the particles has to be from same particles. You can't use different particles. That may affect the efficiency of fluidization.
Sometimes it will help also, it seems. To get smooth fluidization, they take slightly coarse particle, add fine particles. So, then it seems you will get better fluidization. So, this is always counterintuitive, and you get kick when you have counterintuitive things. Automatically what you imagine in your mind and what is happening is same, there is no kick, no.
It's difficult to maintain the purity of the liquid or the gas stream.
Why?
So there might be
because of solid.
because of the interaction with the solid.
Yeah, if you are taking that one as a catalytic reactor, catalyst is the solid particle, right? Where is the purity coming? Because reaction occurs in the particle, inside the particle or outside the particle on the catalyst, and then anyway product will diffuse out and then comes out. What you are talking about, the particles coming with the gas, those we are masters of that. What do you use? Cyclones, not 1, 10 also can use depending on particle size that is coming. So, you can use one first cyclone, second cyclone, third cyclone, 4, 5 cyclones also people use. And beyond that also, if you are not able to take from the cyclones, then what is that use? Filters block, electrostatic precipitators, ESP plants, very common. Okay. So, all those things are there, unfortunately, you are not putting your mind to assimilate your knowledge. I think definitely professors would have told you in particle technology and all that. Deactivation advantage, disadvantage, what you are trying to tell? Actually, when you have a deactivating catalyst, fluidized bed is excellent. Yeah, it is very good. You can take out the particles like water, okay, and then feed continuously. Always, you can maintain some amount of fresh catalyst inside the bed. It is not fresh actually, mixed and fresh. Yeah, regenerator you can use like if you are using like FCC. Okay, take out all the solids, take the regenerator and then send it back. There is another one, because this 1 o'clock. Okay, so this fluidized bed, is it equivalent to CSTR or plug flow reactor? Solids are in perfect mixing condition. Is it disadvantage or advantage for reaction? That is one of the disadvantages. Why? Because concentration gradient is not much. So, what do you do? What do you do to overcome that? What do you do if you want to go towards plug flow? You are using only mixed flows. That is all. So, people use 2 or 3 fluidized beds. Okay. You know how beautifully they use that? They use like this. This is one downcomer, another downcomer, another downcomer. If you are using only 3, this fellow comes out. So, this is gas, these are solids, coming out, solid, solid, gas, gas. This is just CSTR 1, CSTR 2 or mixed flow reactor 1, MFR 1, MFR 2, MFR 3. It is just one above the other. You need not put one above the other, you can also put parallelly. One here, next one, allows of gravity, because it is like a fluid. So, it comes from one bed to the other bed if you are maintaining certain gravity, certain level. So, automatically it comes. So, that is why if you want to, you have to write there non-uniform residence times. When you have mixed flow, you have non-uniform residence times for the solid phase. Okay? That is the disadvantage. Why it is a disadvantage? Because if I take coal combustion for example, right, solids are in the perfect mixing condition. Because of mixing, some particles will come out very quickly, and practically the combustion in that particle is almost, and there may be another particle which is overburnt and then only ash is left. On the other hand, if you take exactly our plug flow reactor, each and every particle would exactly burn depending on the time which you have given, maybe 10 minutes or maybe 10 seconds, whatever. So, that is why you get uniform combustion there, but here also you will get uniform combustion, but at low level. Okay? At low level, because you have at any time coal must be large amount you have to put to compare with the ideal plug flow reactor, correct? No, that is why in fact for a given conversion, why CSTR will be bigger and plug flow reactor will be smaller is the residence time distribution problem. One easy example which you can remember is coal combustion. Okay? So, certain amount I am burning in a plug flow reactor, but if I want to get the same conversion in mixed flow, I have to necessarily use larger bed, because the total amount of solids, some converted, some unconverted, all that must compensate the ideal plug flow reactor, where all solids are uniformly burnt. So, that is why you will have bigger size for mixed flow and smaller size for plug flow for a given conversion. Okay. So, that is why, yeah. So, this is one of the disadvantages, and there is another disadvantage, attrition we told. Okay, that is one, that is with respect to particles, but with respect to walls of the reactor you have attrition, okay, or erosion, I do not say attrition, erosion of the walls, and after some time wall may disappear, shrinking core model. Yeah, wall thickness keep on decreasing because of like shrinking core, and finally disappearing, wall will disappear, because always the solids are moving at very high velocity, it will erode, erosion takes place. So, slightly you may lose some of the material of the wall, and thickness will be smaller. If it is high pressure and all that, it may burst after some time. That is another disadvantage. Okay. So, I think this is fine, and next class tomorrow morning first hour, we will now try to find out what are the parameters you should